Welcome to the lecture for chapter 2.1. We're going to be looking at increasing, decreasing, and piecewise functions, and then a couple application problems. This picture was taken a couple years ago at Christmas time in a beautiful village. Actually, this is in Salzburg in Austria. I'm lucky enough to have a niece that lives there and was visiting her, as well as some dear friends that live in Munich not too far away. And it highlights the sweet nature of your professor. Some people would say I really have horns, not wings, but that's a whole other story. So let's get started. So today we're going to look at how to graph functions, looking for intervals on which the function is increasing or growing, decreasing or shrinking, or where it's constant. Then we're going to look at and estimate the relative maxima and minima, the high points and low points. And then given an application, we're going to find a function that models the application, find the domain and function values, and we're going to graph functions that are called piecewise. The application problem in this lecture is really important because we have to do a substitution. And this is a tough technique for a lot of students, so pay a lot of attention when we get there. So this is pretty straightforward. On a given interval, this just means from one value of x to another value of x. If the function rises from left to right, it is said to be increasing on that interval. So it's kind of like you're going uphill. If the graph drops from left to right, it is said to be decreasing. This is very intuitive, and you can see from this diagram that in this graph, first from left to right, first we're going uphill, and you even see a little green arrow there. It says it's increasing. And then we hit a high point. This is a relative maximum, okay? And then as we hit the high point of the hill, we start sliding down, and you can see that the function is going down. The values of y or f of x are going down, and you can see the word decreasing there. So where a graph goes down from left to right, we say that it's decreasing. And then we hit bottom there in this valley. This is a relative minima, and then we start increasing again until the end of the graph. Very intuitive. Functions that go up from left to right are increasing. Where they go down from left to right, they're decreasing. And it's a pretty intuitive concept. If the function stays the same from left to right, the function is said to be constant. Now this throws students off a lot. This is a function called f of x equals 2. Okay, there's no x in there, so it doesn't matter what x equals. The y value will always be 2, and we have a constant or horizontal line. So if you put in x equals negative 2, y or f of x is 2. You put in x equals 0, f of x or y is 2. Y is always 2 no matter the x values. These are the easiest to graph, but you have to understand the concept. And like we said, that I'm going to give you some math language here now. We're going to look at this concept in a little bit of more of the language. A function is said to be increasing on an open interval. Okay, we've already talked about functions. We've already talked about increasing, going up from left to right. So let's look at what this open interval means. Notice the interval I just goes from one value of x, which is somewhere in the negative area, all the way over to this right side, somewhere in the positive area of x. And notice that there are open circles on the endpoints. And that's why it's called an open interval, because it does not include any values of the function at that endpoint. Okay? So that's all an open. An interval is just from one value of x to another. An open interval just does not include the endpoints. And it just says, this is the math language, if for all a and b in that interval, a is less than b, these are values of x equals a, x equals b. So if a is less than b, then f of a is less than f of b. And that kind of makes sense, right? So as x goes up, the y goes up, and that's an increasing in function. That's all it's saying. If if a is less than b, then f of a will be less than f of b. As x goes up, y goes up, and that's what happens on an increasing function. And that's all this language is saying. If the x value, if x1 is less than x2, then f of x1 is less than f of x2. As x increases, y increases. Okay, that's all that is saying in math language. And this is saying the same thing, but for decreasing. So we have the same function, open interval, and if a is less than b, if it's on an open interval and it's decreasing, then the y of a, f of a, is going to be greater than b. And that makes sense, right? So here this is a smaller value of x, but a larger value of y, because we're coming down. A larger value of x and a smaller value of y comparatively, because the function is decreasing. So as x goes up, y goes down. Decreasing functions, as x goes up, y goes down. That's all this is saying again. All right? And then, of course, we have the same language, the same mathematical language for constants. So again, we have the open interval. You can tell that because we have the endpoints as open circles. And here it doesn't matter what a or b is, what value of x is, because f of a is going to equal f of b. It's going to equal every f of x on that line. So it doesn't matter if x is going up or down. In that interval, the y value stays the same, and that's just a constant function. Okay, so hopefully that language didn't throw you off too much, and hopefully that description helped a little bit. So what are relative maximums and minimums? Again, this is a very intuitive concept, and it just says, suppose that f is a function where some f of c exists, and we have f of c just says that x equals c, and we have three different c values. We have c1, c2, and c3 here on the graph that you can see to the right. And so f of c exists for some x value, x equals c, in the domain of f. Okay, then we say that f of c is a relative maximum if there exists an open interval I containing c such that f of c is greater than f of x for all x in that interval. Okay, now what does this mean? Now we're talking about relative, so it's very intuitive to see this, that I have two relative minimums. And you might think of a relative minimum as a valley. You see one here at C1, and you see one here at C2, okay? We have a relative maximum at that last one was at C3. We have a relative maximum at C2, okay? And it's just saying that in areas close to this f of c value, as long as f of c is greater than all those other f of x values nearby, then we have a relative maximum. If that f of c, and you can see that there, I should have maybe slowed down a little bit. If that f of c is smaller than all of the f of x values in an area around it, the area around C1, or the area around C3, then we say that these values, that f of C1 and f of C3, are both relative minimums. Okay? To me, it's much easier to think of this more intuitively and more visually, where you have a mountain top, that is a relative maximum. Where you have a valley, that is a relative minimum. And you can have a curved valley, as you see at C1, or a pointed valley or a corner valley, as you see in C3. Okay. Later on, we're going to deal with absolute maximums and absolute minimums. And just like the name, it's saying what is the absolute maximum would be what is the largest possible value for this function. So when you look at all the relatives and you look at the endpoints, what is the largest value of y? Or the absolute minimum, when you look at all of the relative minimums and the potential endpoints, what is the smallest value of y? Okay, so again, relative maximums are just any mountaintops that you see in the graph. relative minimums or any valleys that you see in the graph. So let's look at a function here. Again, pay close attention to this function because this one uses a special technique of substitution. A man plans to enclose a rectangular area using 80 yards of fencing. If the area is W yards wide, express the enclosed area as a function of W, okay? So I've given you a graph here. It looks like some fenced area, so it's a little bit green, although it's an unusual color for grass. And most rectangles, for the boundaries of rectangles, we use the dimensions of width and length, okay? So we want to figure out the area as a function of W. That's the actual question. So we need the area formula. Well, the area of a rectangle is the length times the width. Are we done this problem? Was it that simple? No, we're not done, because notice our area formula expresses the area as a function of L and W, length and width. So we really need to get rid of the L. What this question is asking us to do is to express the area really only as a function of W, okay? So in order to do that, we need to get rid of this other variable, L, okay? In order to get rid of L, we need what's called a constraint, okay? Whenever you have an equation or a problem and you want to rewrite it as a function, remember f of x states that function in terms of one input, just x. So if our function is area, we have a problem here because we have two different inputs. We have an L input and a W input, and we don't want that. We just want the W input. In order to get rid of these, we need another piece of data given in the problem that relates W and L. Now, so go ahead and reread the problem and see if you can find it. A man plans to enclose a rectangular area using 80 yards of fencing. If the area is W yards wide, express the enclosed area as a function of W. Do you see it? So the man is enclosing, he's putting fencing, okay? Now, where would he put the fencing? Well, he's putting the fencing on the perimeter. Do you know what a perimeter is? It is the line that you see around the rectangle. That could be the fence, the black outline. A perimeter is the outline. It's the distance around. What would be the formula for the perimeter? Again, a lot of students are so familiar with the area formula that they think, oh, it's just W plus L. Well, think about that. If we built a fence along one side of W and one side of L, would that keep any animals inside the fence? Of course not, because the top and the right would not be covered. So our formula for perimeter is W plus L plus another W for the right side plus another L for the top, okay? And this simplifies into our perimeter formula for a rectangle, which is 2 width plus 2 length. Now, in the problem, it told us that he has 80 yards of fencing, so we can rewrite this as 2L plus 2W equals 80, okay? So if we're going to simplify this, divide both sides or each term by 2. 2W over 2 plus 2L over 2 equals 80 over 2. And we get W plus L equals 40. Now, it's very important that we solve these equations for the variable we want to get rid of. In this case, we want to get rid of the L because we were told to write the function as a function of W, okay? To write the formula in terms of W, okay? So now all we do is we go back to, we solve that first. So subtracting W from both sides, we get the length equals 40 minus W. All we're going to do is to plug the L formula in for L in our area formula. Remember, area equals length times width. But now we have a formula for length, or L, which is 40 minus W. So we just plug this in. And now we have a function of area in terms of W only, okay? And here I've just distributed that so it's more like a polynomial. And we're done. This is very, it can be confusing, but with practice and understanding these simple steps, maybe copy this slide, whatever you need to do, take a picture of it. This is a very, you will use this multiple times throughout the course, and it's a key problem solver about getting rid of, substituting one equation inside of another to get rid of a variable, so to speak, or to rewrite an equation in terms of only one variable. This is another confusing type of problem. These are piecewise functions, and a lot of students don't know exactly what to do with these, okay? Now they're called piecewise because they have different pieces, okay? And all that means is they have different formulas depending upon the input value of x. Okay, so here's one here. So notice that there are actually three formulas. F of x equals x squared for x is less than or equal to 0. F of x equals 4 for 0 is less than x is less than or equal to 2. And f of x equals x minus 1 for x greater than 2. Okay, so there's actually three formulas, three pieces to the function f of x. For these functions, you need to work backwards, and that's why they're more confusing to students, okay? You need to work from right to left. Instead of working here and plugging it in, you first have to figure out, using the values of x on the right, to determine which of the three formulas I'm going to use, okay? So for example, if I said I want to find f of 3, okay, f of 3, which means to find the y value when x equals 3. So I don't just start plugging in 3 to x squared and 4 and 3 minus 1, etc. I go over here to the right and I say, okay, if x is 3, which one do I use? Well, 3 is not less than or equal to 0, so I do not use the first formula, x squared. 3 is not between 0 and 2, so I do not use the center constant formula, 4. And the last formula says x is greater than 2. Well, 3 is greater than 2, so I would use this last formula. So f of 3 would equal 3 minus 1, which would equal 2. So let's do some of these. So what you're going to do here is you're going to say, what is the x value that I'm being asked to find? And then based upon that, you will determine which formula to use. And then you'll plug in your value. So try 3 of these. This is a good chance for you to hit pause, try to find these 3 values, and then check yourself by hitting play. I'm going to continue on now. So for f of 5, whoops, let me stop that. F of 5, this first one, notice again, remember this is f of x, so x equals 5. All right, 5 is not less than or equal to 0. It's not between 0 and 2. It is above 2, so I'm going to use this formula, x minus 1 or 5 minus 1. Okay? So f of 5 means x equals 5. Since 5 is greater than 2, we're going to use the last formula, and we get f of x equals x minus 1. So f of 5 is 5 minus 1 equals 4. F of negative 3, hey, this says x is negative 3. Where does that belong? Negative 3 is indeed less than or equal to. It's less than 0, so it fits in this mold. And so we're going to use the first equation. F of negative 3 is indicating that x equals negative 3. Since negative 3 is less than or equal to 0, the first constraint, we're going to use the first formula, plug it in, and we get 9. So I saved this one for last because it has a confusing element as well, okay? First, we're going to look at what the x value is. X equals 1. It's not less than 0. It is between 0 and 2, and so we're going to use the second function, f of x equals 4. Now remember, this is a constant. There is no x to plug in. So we don't add 1 to it. We don't multiply it by 1. We don't divide it by 1. We just plug in the value. y equals 4. All the time between 0 and 2. Y equals 4. Okay, do not forget that. This one confuses a lot of folks. This is a constant function. So for x between 0 and 2, y or f of x, they're the same thing, will always equal 4. Do not try to add the 1 or subtract the 1, etc. Don't make up your own math. Okay? Now, what happens when we graph these functions? To me, what I try to do is I think about where these boundaries are. So I have a boundary at 0 and 2. So but on the left side of 2, when x is less than, on the left side of 0, we have a boundary at 0. On the left side of 0, when x is negative, we're going to have just the constant value of negative 3. On the graph between x equals 0 and x equals 2, we're going to use this middle formula, negative 3 plus x squared. And then for values greater than, just greater than 2, we're going to use this last formula. All right. Now it's important when I have the same value and less than or equal to or less that I, for example, well, let's do the 2 value because there's no formula there. There's just a constant. Even here in the second equation, I'm going to plug in 0, even though when x equals 0, y is going to equal negative 3. I'm going to plug this in just so I see where that value is. And if it's in a different spot than the first equation, I'm going to use an open circle. And we'll see that in this graph. All right. So we graph f of x equals negative 3 only for inputs x less than or equal to 0. Okay. This is a constant. So we're only graphing from x equals 0, which is the y-axis, to the left. And hopefully you can see that there's a green line at y equals, or f of x equals negative 3. And it goes from negative infinity all the way up to 0. Then we're going to graph the second equation. F of x equals negative 3 plus x squared only for inputs greater than 0 and less than 2. And so this is the next part of the graph between 0, x equals 0, and x equals 2. And this is a quadratic equation. We could pick a couple values. We could pick 0, 1, and 2 and see their values and then graph that. And also we can see it's a quadratic, so it should have a parabola shape. The last thing we're going to do is we're going to graph f of x equals 1/2 x minus 1. A couple things first here. I want you to show you how I rewrote this. To me, sometimes x over 2 minus 1 is a little bit cumbersome. But notice I can pull the 1/2 out in front, and this is the same thing as 1/2 x minus 2. As long as x is in the numerator, I can move it down on the ground by itself, and then I'd have to replace it with a 1 in front, or on top, in the numerator. For whatever reason, for me, fractions like this are easier to do than x over 2 minus 1. It doesn't matter. If the other way is more convenient for you, then continue on. And so now the last part of the graph, from x is greater than 2, we're going to use that last formula, okay? And this is a straight line. This is a linear equation, 1/2 x minus 1, and you can see here. And this is what I'm talking about. Even though when x equals 2, the graph is really part of the second equation, and you can see it here with this closed-in circle at 2, 1. But we still graph the third equation. We plug in the value of 2. We get 2 over 2, which is 1, minus 1, which is 0. So at 2, 0, it's part of the third graph, but it's really not part of the function. So notice that point is an open circle, meaning it's not included. But it is important to include that open circle in the graph so we can see where the boundaries. Now between the first and second equation, if we plugged in 0, we actually got the same value. Negative 3 plus 0 squared is negative 3, and that's why there's not an open circle here, because they actually connect and continue on. Here, there's a different value at x equals 2, and so we include a closed circle for the function where x is less than or equal to 2, where 2 is included, and we include an open circle where x equals 2 is not included. Okay, that's a really important part and often quite confusing. Here's another one that can be a little bit confusing. All right, so we have the function, piecewise function x squared minus 4 divided by x plus 2, for x not equal to 2. And when x equals to, for x not equal to negative 2, my bad. And when x does equal to negative 2, we just have a constant value, okay? So notice this isn't a line, this is a point because we're only given one value of x. It equals or it doesn't equal, okay? Now why did they do that? Well, if we plug in negative 2 into the first equation, we can see it's undefined because we get 0 in the denominator. Negative 2 plus 2 equals 0. You cannot divide by 0, that's undefined. Remember, 0 is your friend, you don't lock him in the basement, okay? But let's look a little bit closer at this first equation. If we do factoring with the first equation, we get x plus 2 and x minus 2 in the numerator, all divided by x plus 2. Well, there we have a common factor of x plus 2 that we can cancel out. So f of x equals x minus 2. So f of x for the first equation really just equals x minus 2 for any value but x equaling negative 2. It cannot equal that. So this is just a straight line. So the graph of this part will consist of a line with a hole at it, with that open circle or hole at negative 2, negative 4, okay? And there you can see it there. So here's our line. Whoops, where's my arrow? There we go. With a hole in it at negative 2, negative 4, okay? And then the graph of the second part, the hole occurs because a piece of the function is not defined. And then we just plot the second point when x is equal to negative 2, y is 3, and we have this point here. And because, again, it's for only one value of x, there's only one value of y, and it's just a point. All right, hopefully that was clear. Do some practice and pay attention to this and watch it again if you need to. The last thing we're going to talk about today is something called the greatest integer function. Pretty simple concept. Here's the notation for it. It looks like a double bracket, and it says f of x equals the greatest integer of x, okay? Now what this means is that you need to pick the integer value. Now integer values are positive and negative whole numbers. Negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3. Those are integers. There's no decimal, there's no fraction. No decimal, no fraction, but they're positive and negative. And so when we calculate whatever the f of x value it is, we do the math inside. This could even be a formula inside, like x squared minus 3, or x squared over 2 minus 4, something like that. Anyway, whenever we find the final value, then we go to the greatest integer that is less than or equal to x. So you can kind of think like the greatest integer as rounding down, okay? So if these were our three answers, negative 5, negative 5.2, negative 5, and 1/8, all of these would become negative 5 if we were looking for the greatest integer, okay? For 0, 0.2, and 1/7, again, we're rounding down. And we get 0. And at 3, 3.2, 3 and 1/8, again, we would round down to 3. Okay? Very simple concept. Know the notation. Understand it. It's greatest integer. And this is where it's a little bit screwy, and sometimes math is. Our mind tends to think of greatest as largest, so we might think of rounding up, but it's really about rounding down. Rounding down. All right, hope you enjoyed this lecture.